Okay, so this is the last tutorial titled Analyze Your ITC Data Using the Advanced Fitting Tools of AFFINimeter. So in this tutorial we will see how to fit data, just one single isotherm, but also how to perform global fitting with AFFINimeter. I will show you one example on this global fitting functionality that we have in AFFINimeter. Just to mention that this tutorial is not going to be that interactive because you don't have the original data series that we are going to use for the fitting, but it would be great if you could practice later on with some data series that you have implemented in your AFFINimeter account already, so you can practice with those curves if you want. Okay, so let's go back to the software, and I will just click on Home to start from a different window. Okay. In order to fit data, we have to go to Project Management in the menu bar, click on Project Management, and again, same as with the simulation, we have in Project Management the list of projects that we have created. And into this project we have the option of simulation, but also the option to add a fitting sub-project. That is what we are going to do now. I'm going to use this project I already have created with the name Tutorial 3. I could start a new project similar to what I did with the simulation, but this time I'm going to start just with this project. So click on Add Fit Sub-Project. And again, we have the option of what project type do we want to fit, sequential binding or independent binding sites. For this tutorial, I'm going to work with sequential binding. And the way it works, the independent sites is similar to the simulation tool. We just need to select the number of sets and sites, and that's it. With the sequential binding, we will have to select the binding model from the list. So name the project and save it, the sub-project. The next step consists in selecting the data series, the isotherm we want to fit. And this is what we are going to do just by clicking on this button, Add Data Series. And the next window is a list of the data series we have in our AFFINimeter account. If you are a new user, you will see you have already a list of examples that you can use to practice, but then you can incorporate your own files. I'm not going to go into this now because well, I think it's quite straightforward and you have many instructions in AFFINimeter. We don't have much time to explain this, so just consider you have already your data series. I'm going to click here to select the latest incorporated data series, and I'm going to select this one, Fit 1. By clicking here, we select the data series and we can visualize it. When we upload a data series to AFFINimeter, we already have to give the information, the experimental information, like the concentrations and the equipment. So once I selected the data series I wanted, it already has all this information and we can visualize the graph. But at this moment we can edit this information. I could change the equipment or the concentration, the temperature. It's not going to be a problem at this moment. I'm not going to change the condition for this example, and I will just click on Next. Logically, the next step is to select our binding model. Just click on Select a Model, and this drop-down menu is showing the binding models you have in your AFFINimeter account. I'm going to select the simple 1-1 binding model. You can visualize it, and if you agree, if everything is okay, just click on Finish. And now we go back to our Fit subproject, but where we already have the isotherm we selected. And in this window, we have three tables. Tables describing the experimental settings that we cannot modify at this moment. A table down here that we call table of reaction parameters that contains the information about the thermodynamic parameters associated to each equilibrium that is described in our binding model. We have a 1-1 binding model, and we have just one equilibrium, and we have association constant and enthalpy change. By default, these two parameters are set as fitting parameters. As you can see in this box, fit, the box is checked, which means that during the fitting procedure, they are fitting parameters, variable parameters that we want to know. Additionally, we can set up an upper here or lower limits, upper or lower values of these parameters, both the association constants and binding enthalpy, and also we could choose an initial value or seed to start with in the fitting procedure. But as Angel was mentioning before in his talk, an advantage of AFFINimeter is that we even don't need to include this seed. We can just leave this RND, which stands for random value. So we don't need to include a seed that somehow should be close to the final value of the parameter. So I will leave these reaction parameters like this. I'm not going to do any change. And let's have a look at this other table that is called global parameters, and that is describing parameters that account for artifacts that may modify the shape or somehow the information contained in the isotherm. We have this parameter that we have the QDIL that stands for the molar enthalpy of dilution of the titrant when we inject it into the calorimetric cell. And this parameter is important, especially when we don't have a blank experiment of dilution of the titrant. So in that case, we can just check the box fit for this parameter in order to correct this artifact, right? Deviation of the curve coming from this thing, this issue. We have the parameter Q that we call QDB, that stands for deviations in the isotherm, in the form and the shape, coming from artificial artifacts that somehow we cannot control, like for instance something happening with the instrument at some point that makes a weird shape, or some things like that. So this parameter is to correct this type of deviations. And finally, we have here a very important parameter. Angel and Juan, they both talk about that, the parameter R, that is defined for every single compound that is participating in our binding model. In this case, we have an interaction between M and A, so we have two R parameters, RM and RA, and this parameter R stands, accounts for differences between the nominal concentration of that compound, the species, and the real concentration that we have in the experiment. The nominal concentration is the concentration that we think we have and that we include in this table. The value is 1 when there is no difference between both concentrations. So for this example, Well, let's consider that I don't know exactly what is the active concentration of M. Let's say I have a protein and it's not fully active, which is quite common, but I don't know exactly the percentage of activity. So what I'm going to do now is to set Rm as a fitting parameter, clicking on fit, and I will consider that the value R should be between let's say 0.5 okay, 0.5 and 1. Okay, so I think we are ready at this moment to run the experiment, and just click on run. This is a window just to let me know that I'm using, that I'm paying for, that I'm using one credit, right, to run this experiment. The number of credits you use depend on a series of parameters, like for instance the complexity of your analysis. Just click on OK, and the analysis should take about between 1 or 2 minutes. This window will show you a bar of the progression, as you can see here already. And because we don't have much time, well, you can see this goes pretty fast. But I performed the experiment before, so I have it ready in another sub-project. So I'm going to just show you the results. As you can see, the experiment is running, and this is the same experiment already performed. I will click here to visualize it, and this would be the result. So what I have in the results window is the graph corresponding to the experimental data. The fitting is really good because, in fact, this experimental data comes from a simulation just designed for the tutorial. Okay. So we have the experimental data, and overlap we have the red curve corresponding to the best fitting. We have the information of the parameters that were fitted, Rm, Ka, and delta H, with the corresponding uncertainty that can be visualized in terms of standard or statistical deviations. And very interesting, we have also a list of local minima that are potential local minima, a list of 10. That's the software found throughout the fitting. This table, in our opinion, is very important because it's giving us a lot of information on how well you can trust the results. For instance, this fitting looks very nice, it's very good, and it has very nice chi-square value. And if we have a look, well, this is very small, but just trust me, the chi-square of all the local minima calculated is the same basically as the chi-square found for the best fitting, and all the values, the R, K, and delta H, are equal and correspond to the best this best fitting. So this is telling us that, in fact, in this case we have, or the software found just one local minima, which is very good. I forgot to tell you before that if we click here on top of the graph, we can have a look at the complex species distribution, the same graph we had in the simulation tool. I will go back to the isotherm. No questions so far? Well, so now I'm going to do something else. I just can rerun the experiment anytime I want by clicking here on this button, Fit Settings. So I go back to the window where I can do modifications in the settings for the fitting. And let's consider that I don't know either what is the exact concentration of A. I have a solution of A, and someone told me that that it is prepared with a concentration that has 10% of uncertainty. This means the only thing I can do is to consider RA as a fitting parameter as well. So as you can see, this is very nice that we can just try to include these deviations of the concentrations for all the species participating in the binding event. And I will just leave the minimum and maximum values in 0.9 and 1.1. And I will not modify, I will not make more modifications, just run. Click on OK. And again, we have a little bit of time waiting. And again, I will go directly to the results. Let's wait just for 1 second, see if we have the progress bar already. So let's go to project management, and it's going to be fit 2. Okay, so this is the result of this next fitting, and as you can see now, I have fitted both R parameters. Initially, I had an RM of about 0.8, like 80% of the protein was active. Now the result is slightly different, not quite different, but slightly different, because I'm considering RA also as a fitting parameter. And I have also slight differences in the association constant and the binding enthalpy. But again, the fitting is quite good, and it's good also. It should be even better because I'm considering more variables in the fitting. This is a chi-square, and if you pay attention to the local minima, now we have a difference from the previous experiment. Here, like the chi-square of this local minima is similar or the same as compared to the best fitting, but now the values of the fitted parameters are different. Some of them are different from the best fitting, and also different between them. For instance, if you pay attention to the Ka or delta H, are in both R's. So what is this information telling me? This information is saying that we have many or different local minima that are also that fit very well to the experimental data. And this is happening because we have too many variables, so we can combine values to have a very good fitting in all the cases. So what we have is an over-parameterized system. And so we cannot really trust this data because any of these results could be good enough. So what can we do in this case? Well, what we have to do is to increase the number of experiments. So we are going to increase the ratio number of experiments versus fitting parameters. And this is the starting point for the next example. Yes?
I wonder if that uncertainty could be somehow reflected in the standard deviation of the best parameters. It would be nice, because I would think that most people will not look at that table, and they will just look at the standard deviation that is associated in that row, and that one is really, really small, although there are several solutions.
Yeah, well, it's very, very small because, we are working with the simulation. But, yeah.
There are several solutions.
Yes.
So the standard deviation with the parameters should be large.
Yeah. I think we could do that, Angel, maybe, like to consider...
Evaluation, just comes from the corresponds to the best solution. Yes, it's not an average of those values. You can download this table and you can calculate the average of the solutions corresponding to each parameter, and the standard deviation getting in that way will be different from the standard deviation in that plot.
I understand that. I was just wondering, it's just a suggestion that if that uncertainty could be somehow embedded in the first row, it would really help.
Yeah. Thank you. I think it's a good suggestion. Yeah.
Thanks. Yeah, in fact, as Angel was suggesting, by clicking in this icon here, download. Oh, sorry, yeah. So I'm a little bit tired already. So by clicking on download, but just by clicking on downloads, we can download the table. And by clicking on this icon, we can visualize the fitting corresponding to that local minima. So, yes, I was saying that, yes?
I can explain to you in detail how it is calculated later. It corresponds to a fitting of all experimental points, but removing just one at a time, and then repeating the fitting without this point. And then from the standard deviation of all these fittings, which are the same number of fittings as the number of points in the plot. So even if I remove one point at a time and repeat the fitting, starting from the seed corresponding to that solution, I get always the same solution. That is because, those data correspond to a simulation. It's only because of that.
So the standard error that appears there is not from the fitting?
The standard error comes from the fitting, from the covariance matrix, but the statistic error comes from this other method. Yeah.
Okay, so for the last example, I would like to show you how to perform a global fitting, and what I'm going to do is to include one more isotherm to this experiment, to the same experiment, to show you how we can improve the results using global fitting. So just go and click to Fit Settings again. And in the Fit Settings window, we have this button, Add Data Series, that let us incorporate more data series, as much as we want. I'm going to add just one data series, but we have even tried, I think the most we reached, I think it was an experiment with 24 data series. We perform a global fitting with good results, I have to say. So I just click on Add Data Series, and I have again the list of data series that I have in my AFFINimeter account. I will click here to select the last ones I incorporated, and I will click on Fit to here in this icon. Again, I visualize the data series, and at this point I can modify the experimental conditions that I included when I uploaded the data series for the first time. I'm not going to do to perform any change, and just to let you know that this experiment consists on exactly the same experiment as the previous one, but in this case we knew the exact concentration of active ligand of M. We had the chance to, let's suppose that we had the chance to measure the activity, right, by other means of this compound. So I will just click on next. Again, I have to select the model, because one thing we can do with the global fitting, which is very useful too, is that every isotherm has link its own binding model. We can globally fit different isotherms that follow different binding models, binding interactions. Click and select. I will, in this case, we have the same experiment. We have a 1-to-1 binding. Click on finish. And now we are in the window of the sub-projects, and you have the two isotherms. This is the first one, fit 1. The second one, fit 2. We are keeping the conditions we set in the last experiment, and now we have to define the new experimental, the new setup. So as I was saying, now this time we know that Rm is going to be, we know exactly the concentration of the active compound M, and in such a way that Rm is going to be 0.9. That is 90% of M is active in the calorimetric cell. The solution of A is the same as the one I used for the experiment 1. And again, I'm not sure about the exact concentration of species A. So I'm just going to select to check this box, fit. And I could do that, but now I realize that in both experiments I should have the same results of A, of R, because it's the common parameter, right? So what I have to do instead is to link this parameter RA in experiment 1 with this parameter RA in experiment 2. We can do that with the linking parameters function. This blue button, just click on link parameters and click on the box corresponding to value of RA in this experiment, click, and then click on the same box of RA of the second experiment. And what you see is that now this box is filled with RA parenthesis 1. This is telling me that I'm telling the software, let this value be the same as this one throughout the fitting. And I have to uncheck this box, of course, because we are linking these parameters. Just click on done. And I can do the same with the association constant and again with the binding enthalpy, because again I should obtain the same results. So I have to click on link parameters again, click on this box in the association constants, click, and on the same box in the other experiment, and you will see that now it says K11 corresponding to this association constants. Click on done, and in order to link the enthalpy parameter, just click again on link parameters, click on the box corresponding to the enthalpy of the first experiment, and then to the box in the second experiment. Click on done, and don't forget to uncheck the fit option here in the association constant and the binding enthalpy of the second experiment. So I think we are ready at this moment to run the experiment, and now what we have is two isotherms, two experiments, and we have four fitting parameters, one association constant, one binding enthalpy, 1RA and 1RM. Before, we had 4 fitting parameters, the same number, but just one isotherm. So we should just run the experiment, but before we do that, we need to increase this parameter. That is called the number of repeats. That is a parameter associated with the number of curves too. Well, I will not go into details on this parameter. I think it belongs to the more advanced tutorial, but I will just increase it because I have 2 isotherms to fit instead of 1. Just click on Run and click on OK. And again, I have the result already prepared. Let's see if the fitting starts. Just 1 second or 2. This experiment will be a little bit longer because the fitting is the complexity is higher, but you see it's already running. So let's go to project management, and it's going to be fit 3. Okay, so this is the result of the global fitting, and this result is telling me that 95% of the species A, like the difference between the nominal and the real concentration is 95%. The species M in the first experiment is 75% active, and I have global results of the association constants and the binding enthalpy. But the most important information in this case, in this example, is about the local minima table. In this case, we have again chi-square, very similar, the same, basically to the best fitting, to the best global fitting, and now all the values are the same. So this is telling me that this way, with the global fitting, I was able to perform a robust analysis by increasing the number of experiments. And well, this is a very powerful tool in order to get good data, because sometimes you need to fit the isotherms to complex models with many fitting parameters, and we have to know very well what have to do in order to get good results. So it's not just a question of designing lots of binding models, but we also have to know how to use it and how to design our fitting in order to get good results. So we are about to finish the last tutorial, and before finishing, just show you one last example that is already done. Okay, let's see. So this is just another global fitting. I will explain you very fast, just to show you that we have performed the easiest or the simplest global fitting with 2 isotherms, but we can do much more. We can, as I was saying, we tried successfully to globally fit 24 isotherms. And we can also perform global fitting where the binding model changes with the different isotherms, and also we can use more complex models. For instance, this is the case of a global fitting of 2 isotherms that describe a competitive interaction between ligands A and B competing for the formation of a complex with M. So in this case, we had 2 equilibria, and what we perform is a direct, the classical direct experiment where we have a mixture of ligands A and B in this range, and this is not giving us much information. Even it could be fitted to a 1-1 binding model, relatively good. And so we could perform the reverse titration where the mixture of ligands is in the cell, and this curve is giving us a better idea of what's going on, and so we can perform a global fitting of this situation, for instance, without any problem. So with this example, I'm finishing with this tutorial. I don't know if you have any questions or comments or advice on how to improve the information we provide here. Yes? We are working on it right now. It's not implemented right now in AFFINimeter, but it will be in the next future. And okay, so I will finish this series of tutorial just with a brief reminder that we would love to keep on providing more tutorials on the software AFFINimeter. For instance, advanced tutorial and complex binding models, so add more complexity to the fitting and the use of AFFINimeter. Advanced tutorial on global fitting too, showing more complex cases, and of course on how to get kinetic information from ITC experiments with KINE-ITC. We are working at this moment in the development with Philippe Dumas about this very interesting functionality. Yes?
Regarding global fitting, what is it implementing the global fitting of isotherm at different temperatures? Because for KINE-ITC it is extremely important. So I forgot if it is implemented right now or not.
You mean the global fitting at different temperatures, including the Van 't Hoff equation? Yeah. Okay, that is not implemented yet, but it will be. Yeah. Actually, we want to do that in a more general way. The idea is to include global parameters, which can be added by the user, and then we can have more than that, because we can have the Van 't Hoff equation and many more restrictions.
Any other question? No? Yes, Daniel.
Here you have asked for one titration approximately 20 to 30 or 60 points each titration. But for the KINE-ITC, when you have like for 2 hours experiment, you have 7,200 points. So how is the data treatment or with the AFFINimeter on the cloud?
That is a very good question, because we are working on that with Philippe Dumas, and we are working on that with different approaches. One of them is to translate the load of the processor to the user using JavaScript. So that is the easiest way, and this way is the implementation we already have under progress. And the other way is to work on the cloud. We can do both things, and I think, well, we will see. But it will be ready, I hope it will be ready in approximately 1 month. With Philippe? Yeah. In 1 month we'll have the first version of yeah, okay. Depends on the length of the month, okay.
Right.
So then we will have a tutorial on KINE-ITC and test the cloud stability,
yeah, probably. Yeah, thank you.
Okay, so thank you very much for your attention, and we're about to finish with the workshop, and well, before finishing, Juan is going to say something. Okay.